And systems to holistic solutions. So at universities today, we teach students and we teach young professionals, always think of the big picture. Don't just think of the component. In other words, the protective relay in the substation. But that device has two-way communications and can be a node in a larger network. Okay? So we think of the holistic solution. And in a minute here, I'll show you 6 examples of holistic solutions. Holistic means company-wide, and not just for a particular group in the organization, but for the whole company. And a solution is a set of technology components integrated together to successfully interoperate to meet the business needs of the customer. Okay. Now, success is, I say success is like a 3-legged stool, right? A stool that has 3 legs. Each leg is very important. If one leg is weak or missing and you try to sit down, you will fall over. In other words, we need all 3 of these to be successful. And it's technology, standards, and policy. So technology today must be standards-based for successful integration and interoperability. And policy is the strongest driver today to encourage or incentivize a customer to purchase our technology. So we spend a lot of time with policymakers and making sure policy is strategic for our company. With everything that we do, we want the grid to be flexible. Ideally, we want it to be able to self-heal and reconfigure. So self-healing, we have logic we can put on the distribution system that will automatically detect the fault, locate the fault, isolate the fault, and restore service around the faulted segment, all automatically with no person involved in a minute or 2. So we have the capability today to be self-healing, particularly on the distribution part of the grid. And we have remedial action schemes on the generation transmission part of the grid they have certain trigger points that they look for. And when any of those occur, there's a series of steps and logic that they implement, right? So, the more self-healing we can be, the faster we can address, the faster we can take care of a fault and prevent it from cascading and becoming a more serious problem, right? So the next point is resiliency. Grid resiliency is very important today. What is resiliency? Well, resiliency is the ability of the grid to withstand stress. And stress can be from an extreme weather event, like a monsoon, a hurricane, or tornado, an ice storm, right? How well does the grid withstand that stress? So we can, when we design things for the grid, like architectures, we look at redundancy, right? We look at reliability, but the true test, how well we did, is when the grid is stressed. How resilient is it? How many outages have occurred? How many people are without electricity? What's the duration of the outage? So this is something that's very important. And today what we find is that many utilities are implementing strategic microgrids. So instead of having one homogeneous grid, you can divide up the grid into strategic microgrids. And a microgrid may have its own generation, which may be renewable generation, so that if it is islanded, it has enough generation to continue to operate independent of the larger grid, right? That's ideal. So you have a lot of islands that can disconnect from the main grid and continue to operate. Okay, and then we're going to talk a lot about big data. That's a trend today. And with big data is analytics and the user experience. And what we say is the journey to digital transformation, which is the goal of a utility today, is have a fully digitized grid with greater connectivity and a robust communications infrastructure. Many of the components today of an automation system are cloud-based, right? We're using the cloud to a much greater extent. And also we're using social media to a greater extent. Instead of the electric utility assuming that when a customer has outage information, instead of using a telephone, most customers would prefer to interact with their utilities with social media, for instance, Twitter. And you know, my electric utility, for instance, here in the United States, could have my Twitter handle in my customer record. And so when I tweet information, maybe outage information to the utility, they can use my Twitter handle to find my customer record. And then in my customer record is my property address. Okay. So I don't necessarily have to call them from home with a landline phone number, but I could be anywhere and use social media. And then one thing that's very important is convergence of two groups within the electric utility, the IT group, information technology, and the OT group, which is operations. We need to have them seamlessly work together so that we can do effective enterprise data management. We have valuable data on the operations side that we need to bring across the firewalls and over to the corporate network, so many other groups in the electric utility can use that information. Okay, so let's look at smart grid concepts. And we'll get back to the importance of the convergence, or the bringing together of the IT group and the OT group, IT and operations. So we're integrating the electrical and information infrastructures. Now, the result of that would be improving the reliability of the grid, the operational performance, and the overall productivity of the workforce. Increases in energy efficiencies, decreases in carbon emissions, empower consumers to manage their energy use and save money without compromising their lifestyle. This is very different, but something that's going on all over the world. And optimizing renewable energy integration and enabling broader penetration of renewable generation. So in the lower left here, one thing with smart grid is there much more focus on the distribution part of the grid. For many years, most of the investment and spending was on generation and transmission and very little on distribution. And that's changed, right? We have a lot more focus on the distribution part of the grid today. So I like to differentiate, we've been adding intelligence to grid for many years. In my 47-year engineering career, full-time work, I've been adding intelligence to grid with the companies I worked for a long time. So the concept of smart grid isn't new. And what I'm showing on this slide is shaded in gray, which I call old grid, is what we've been doing previously, prior to smart grid. Different parts of the grid, the intelligence that we've been adding. And shaded in light green is the new things that we're doing with smart grid. So you can see on the bottom here, I've shaded voltage control halfway because we've been doing independent voltage control and reactive power control for many years. Voltage is directly proportional to load. So if we want to lower the load, we can lower the secondary voltage, right? And we do this like on a hot summer day, if it's a summer peaking utility, then and if the utility doesn't want to exceed their previous peak, then we can lower the secondary voltage. Okay. Also, we can switch capacitor banks on the distribution feeders for reactive power control or VAR control. The difference today is we've integrated these two together. We do integrated voltage and VAR control on a distribution management system or as a separate application at the substation level. We, a lot of focus today on integrating renewables on the grid. We go up to the middle row. You can see sensors is shaded halfway. We've been adding many sensors on the grid for a long time, but the difference today is we have many what we call specialized sensors. Lots of technology, lots of functionality, and the ability to do some special sensing. For instance, this one that I show here is a sensor that I would connect to a transformer, and the oil in the main tank of the transformer would be flowing through the sensor. And this sensor can detect gases dissolved in that oil. This is very important. This is called dissolved gas analysis. And we have sensors today that can detect up to nine different gases in the oil of the main tank of the transformer. And the presence of a specific gas is telling us that a certain failure mode is occurring in the transformer. So if I see methane, if I see acetylene, if I see ethane, these different gases, I know exactly what is failing in the transformer. And then I look at the rate of change of that gas, and that tells me how serious the problem is. Is it degrading quickly, or is it more of a slow degradation? Okay. Then distribution management, as we integrate more renewable energy or distributed generation on the distribution part of the grid, that part of the grid becomes very complex. We'll talk more about that. And to manage that increasing complexity, utilities are installing a distribution management system, or sometimes we call it an advanced distribution management system, or ADMS. And then if we go downstream of the substation, we get into what we call distribution automation or feeder automation. And this is where the biggest benefits occur for the utility. For every dollar we spend on optimizing the distribution part of the grid, we get typically $5 to $6 back. So it's a very strong benefit to cost ratio. Then we'll talk more about smart meters and the information that we get back from smart meters. So this is a very important slide, and the notion of a smarter grid. So we have a smart grid, what we've been doing for many years, the intelligence we've been adding, but then we want to distinguish that from what we've been doing more in the near future. Holistic solutions, I talked about that with what are the key trends. And I want to show you 6 holistic solutions. And the thing with a holistic solution is that we have a lot of technology components, devices, and systems that we can integrate in different ways. But the question is, what has the most value to the customer? Okay, that's important. And so this is an example of 6 holistic solutions that have strong business cases. The first one, asset optimization. Instead of waiting for an asset to fail, which is really what we call reactive maintenance, right? You wait until something has a problem, something fails, and then you react. The problem with that is that it's too late many times, the transformer has exploded, the circuit breaker has failed, and there's an outage, right? An unscheduled outage. So with asset optimization, we said, let's be smarter about this. Let's be more proactive. And let's figure out what health information we need from the asset, what analytics we need to analyze that health information, and let's predict that a problem is going to occur, and let's prevent it from occurring. We don't want the asset to fail. We don't want to lose the asset to an explosion or to a fire, right? We want to protect it. Think about a transformer. Transformer is a multi-million-dollar asset, very expensive. So if you look at the business case, if we can delay the replacement of $1 million transformer by 2 years, we've saved 10% of the price of that asset. We've actually saved $100,000 just in delaying the replacement by 2 years. So that you can imagine the business case for doing asset optimization is extremely strong. Okay, the return on investment and the payback period is very short, typically only a couple of years. So there's a lot of work going on today in what we call remote monitoring and diagnostics, M&D, and asset performance management, or APM. Okay, and this is where we get into, it's part of the journey to digital transformation of the grid, and where we get into artificial intelligence, machine learning, and a concept called a digital twin, where we combine the physics of the asset with the health information of the asset, and we can simulate the asset through what we call a digital twin. So with asset optimization, we started with transformers, and now we're looking at optimization health of high voltage and medium voltage circuit breakers. Okay. Second is demand optimization. Here we take aggregated load and we can use that as a dispatch tool in the control center. So instead of doing traditional automatic generation control, where we're ramping generating units up or down based on changes in frequency and changes in tie line interchange, real and reactive power, we can pull the trigger, or we can change the load. We can turn some load off, but in a controlled manner, so that the customers really don't feel the difference. Okay, and we've done that very effectively, and it's a very important dispatch tool in the generation transmission, or EMS, control center. Third is implementing smart meters with the two-way communications with metering. Fourth, I mentioned distribution optimization. This is actually the strongest business case today because of the previous lack of investment in distribution. And secondly, typically the power factor on the distribution part of the grid is not very good. There's a lot of room for improvement, and that's why the benefit cost ratio is so strong. I mentioned it's 5 or 6 to 1. For every dollar we invest in distribution optimization, we get $5 to $6 back. So there's a lot of focus today on distribution, which I'm going to talk about here. And then second strongest business case of these 6 would be asset optimization. Fifth is transmission optimization. Here we're doing a lot of work with synchrophasers, or what we call phasor measurement units. It gives us a lot more insight into what's happening on the grid. When we use typically SCADA data, SCADA data is data every 2 to 4 seconds, right? And that's what we typically use on the grid. 2 seconds, 4 seconds, 6 seconds, whatever the scan rate of the SCADA master station is. SCADA means supervisory control and data acquisition. A SCADA system is the platform for all automation, okay? SCADA, extremely important. Now, I've co-authored 5 books. One book is on smart grid. I wrote there's 25 chapters in that book. It's over 800 pages. And I wrote the last chapter on the future of smart grid. But I co-authored a book on SCADA called Power Systems, SCADA, and Smart Grids with Professor Minnie Thomas. Minnie was a professor at Jamia Millia Islamia University in New Delhi, and that's where I first met her. But she's on a 5-year assignment right now as the director of the NIT in Trichy. Okay, and Minnie, I first met Minnie about 20 years ago, and we spent over 2 years writing a book on SCADA, 335 pages on SCADA, that was published in 2015. So SCADA is the, as I said, is the fundamental platform for all automation. If it's a SCADA system for generation transmission, it's called an EMS, Energy Management System. And this is where we get into transmission optimization with an EMS and taking synchrophasor data, which it gives us 40 to 50 samples per second, okay? So you can see if we use SCADA data, it's every 2, 4, or 6 seconds. But with synchrophasors, 40 to 50 samples per second. And that gives us a lot more insight into the behavior of the grid. And to finish my comment, if it's a SCADA system for distribution, this is where it's called a DMS or an ADMS. And we'll talk more about an ADMS, okay? And then lastly is workforce and engineering design optimization, right? Our goal is standard engineering designs. It saves us a lot of money. There's less risk with schedule delays, with cost overruns. And with the workforce, what's very important with the workforce, in many countries in the world, we have an aging workforce. So we say in our industry, we not only have an aging infrastructure, but we have an aging workforce. For instance, in the United States, in the next 5 years, 40% of all the employees and 60% of all the executives in the energy industry will retire, okay? And so what's very important is that we plan for that. Now, what we have to plan for is that the value of what we do in the real world, in our work, is an art. And it's very different than what we did as students or what students do at the university. What we learn at the university is the science of what we do. It's reading books, taking courses, working with professors. Anybody can do the science, okay? And we can do that with books. But the art, the art of what we do requires years working with experienced people, okay? You can't do it overnight. You can't develop the art, you know, by reading a book. You have to spend years with experienced people. And that's why when experienced people retire and take all that experience with them, we want to make sure we capture that before they retire. So that's why we have many mentoring programs today. You know, I mentor many students and young professionals all over the world. We need to transfer the art of what we do to students, to young professionals before it's lost, right? Before the retirement occurs. And when I took over as IEEE Power and Energy Society president in 2006, the average age of the PES member was over 50 years old, and the average age of the IEEE member in general was 42. Okay, so we had we needed to attract more students and young professionals into the Power and Energy Society. At the time, the name of our society was Power Engineering Society. And we found that to attract more young people, we changed the name of the society in 2008 to Powered Energy. And by energy, we emphasize that we help society, we help the environment, right, with renewable energy, with solar and wind. And we've been able to attract many, many young people into PES. We used to be the third largest society in IEEE. We're now the second largest with over 40,000 members and only 10,000 members from being the largest society. And the largest society today is the Computer Society. So as we continue to grow, we may we may be larger than Computer Society and someday be the largest society in IEEE. Okay, but this workforce is a real issue. We need to capture the experience of the senior people and transfer that to students and young people before the senior people retire. Okay, so let's look at these 6 holistic solutions at a high level, and let's look at the technology roadmap of the 6 solutions. So remember, I said in the beginning, a solution is a set of technology components that are integrated together to successfully interoperate to meet the business needs of the customer. So if you look at, just take one of these holistic solutions, take distribution, light blue boxes. You can see the set of technology components that are part of the distribution holistic solution. In the upper left is the office or the control center. In the lower left is substations. In the middle, lower is equipment on distribution feeders. And all of these are from different vendors, but they all have to successfully communicate with each other and exchange information with each other. And that's not trivial. It's not easy to do. Okay. So this shows you why we teach students today and young people always think of the big picture, not just one blue box, but each of these boxes has two-way communications capability and can be a node in a network. And it's the holistic solution that has more value to the customer than the individual component, technology component itself. All right. One other point, this also shows the importance of communications, of greater connectivity, right? And what I emphasize today is that we need a strong grid before a smart grid, okay? Strong grid before smart grid. Don't buy a lot of new applications or a lot of new equipment and install it when the foundation of your grid is weak, okay? A strong grid is needed first. And by strong grid, I mean a robust communications infrastructure and a seamless IT infrastructure where OT and IT work closely together. Remember, communications is the enabling technology that allows us to automate. So when I was a student, electrical engineering student, and I really enjoyed power system analysis, power engineering, and wanted to specialize in power, I learned very quickly that I needed to study communications because I love power system automation. My whole career has been adding intelligence to the grid and automating the grid, almost 50 years. But to do that, we need communications, and we need all kinds of different communication technologies. A communications infrastructure for electric utility is a hybrid set of many, many technologies working together. And, the communications has to support the response requirements, the latency requirements, the bandwidth requirements of each of the applications. So don't, let's make sure we have a strong grid before we think about smart grid or before we think about adding anything new. So integration, interoperability are very key. And this is some examples here. Smart meters, we can get the voltage from a smart meter and include that into the distribution management system in the network model. And we do that when we do volt-var control, because we need to make sure the voltage at the last customer is within the range that's for the standard in our country. In the United States, we have a standard that says the voltage at the customer must be 120 plus or minus 5%. And so we need to make sure, particularly if we have a long feeder with a lot of voltage drop, we need to make sure that the voltage at that last customer is within the range, okay? And all smart meters have a capacitor that is charged when the meter is energized. But when an outage occurs, there's enough charge in that capacitor for one final communication from the smart meter to the utility. And we call that the last gasp communication. And that's reporting the outage upstream to the outage management system. The geographic information system is the reference system for the network model for outage management and distribution management. We take status changes in the distribution management system and send those to outage management. For instance, if a feeder breaker trips, we know that all the customers on that feeder now have an outage. And so that's very important information. That one status change can tell the outage management system all the customers that now have an outage, right? And then I mentioned that we want customers to transition from using the phone to report outage information to the utility to using social media, okay? So we see a lot more microgrids today, a lot more distributed generation. But the challenge with that is that when we design the distribution part of the grid, what I'm saying in the lower part of the slide here, the distribution controls and protection took advantage of and were designed for assuming that electricity was flowing in one direction from source to load. In other words, for many years, if you were a field worker with an electric utility and you were going to go out to do some work on the distribution part of the grid, the feeling was, right, the rule was that before you did the work, if you open the upstream device only, like a switch, if you opened it upstream, then you had a safe working situation because now everything downstream was de-energized because electricity flowed in one direction only from source to load. That's not true anymore. As we integrate more and more distributed generation all along the grid, now we have two-way power flow, okay? Very complex. We have possible congestion. On the next slide, I'll show you some of the challenges, but the unique challenge now with the distribution part of the grid is two-way power flow, and I'll talk more about voltage regulation concerns. Now we can integrate renewable energy in three different parts of the grid: at the transmission level, the distribution level, or the end user level. And at the end user level, it might be photovoltaic panels, right? Solar panels on the roof of a home, as an example. So let's look at what we'll do is we'll primarily talk about integration at the distribution substation and at the end user level, okay? So some of the challenges are open circuit over voltage due to unintentional islanding, protection ratings that may not match fault currents. So as a protection engineer, when we need to determine the protective relay settings, we will do a short circuit study. And so we'll model the grid and do a short circuit study and simulate faults occurring to determine what the magnitude of the fault current would be at different parts of the grid, so we know what the protection rating should be. The when we do that short circuit study, though, we typically would only look for the contribution to the fault from the source side. We typically would not model the load side contribution. The challenge, though, is as the penetration of distributed generation increases, becomes more significant, we will have a significant contribution to the fault from the distributed generation, from the load side. If we didn't model that when we determined the ratings of the protection equipment, then we may have protection ratings that don't match the fault currents. And this has been a problem. Also, the load side contribution, the varying fault currents due to distributed generation are varying, right? They're changing because of the intermittency of the renewable, of the distributed generation. The sun isn't shining all the time. The wind isn't blowing all the time. So the load side contribution to the fault varies due to the intermittency. That complicates things even more. Okay, and then we'll talk more in a little bit about the stress on voltage regulation equipment. So we see more microgrids today, and originally with the concept of a microgrid, I called it a niche technology. And the three niches where we had originally implemented microgrids were university campuses, military bases, and rural villages. And this, what I'm showing here, is a microgrid installation we did at GE for a rural village in Canada, in British Columbia, Canada. And you can see that the rural village, this rural village, by the way, was not near any electric utility. So it had its own hydrogen fuel cells, had its own photovoltaic panels, had its own hydro generation, but its base generation was diesel, actually is diesel. And, the cost of diesel fuel and the cost to transport the diesel fuel to a rural village is very expensive. Also, when the diesel generator operates, it sends carbon dioxide to the atmosphere, pollutes the atmosphere. So, we want to minimize the use of the diesel generators and maximize the use of hydrogen fuel cells, the solar generation, and the hydro generation. But we also want to make sure the residential and industrial load are satisfied all the time. So we took a microprocessor-based relay, protective relay, and with GE, this was the U90 relay, and we added logic to the relay to become the microgrid controller. And then you can see that throughout the microgrid, we have blue boxes, which are high-speed communications equipment. So every 2 seconds, we know exactly what's happening, and we're optimizing the operation of the microgrid. Okay. So we see more microgrids today being used, as I mentioned before, with respect to resiliency. Strategic microgrids being implemented to help make a utilities grid more resilient. So there's a lot of focus today on microgrids. Okay. Now, we talked about the intermittency of distributed generation. So, well, this is variable generation. And there's a big difference between variable generation and non-variable generation. We can take a thermal power plant, whether it's a coal-fired or oil-fired or a nuclear plant, and we can base load that and keep it at that output level, and it'll stay there to satisfy the load. And we can use it to regulate the grid, right? As the frequency changes, system frequency, as the tie line interchange changes, we can use thermal power plants or hydro power plants to regulate the grid. Problem is with variable generation, we don't know what the output's going to be. It depends on the sun, depends on the wind, and we really can't regulate the grid with those because it's tough to forecast, right? It's tough to know what the output level is going to be. So we monitor variable generation, and the challenge for us is that when the sun's not shining or the wind's not blowing, the customer still wants electricity, right? So how do we still bring electricity to the customer when the sun is behind the clouds or the wind stops blowing? So we have to compensate for the variability, and we can do that with energy storage. In the middle of the slide here, we call it bridging storage. We bridge the intermittency. But again, that depends now on the application. If it's for frequency support, we need that storage instantaneously, right? And a good chemistry, a good energy storage chemistry for that is lithium ion. So that's more of a power need, instantaneous. If it's more of a longer time need, that's more energy related, or the integral of power, right? We take all the power points and we integrate that, or the area under that curve. The integral is energy. That's longer time need, and there we might use different chemistries. We might use sodium sulfide, okay, for energy storage. So, we really have to look at the energy storage applications. We have to look at the time domain, the time requirement, and choose the best chemistry. In addition, we need, and we have now, fast start, fast responding, natural gas-fired thermal generation, specifically designed for variable generation to help us with variable generation. And I'm showing some Flex Efficiency 60. This is a GE thermal generator that's designed to be installed with variable generation. So another thing, we're seeing, I mean, it's obvious that there's more and more installation of distributed generation. The penetration is growing, which means that we have to have new technology solutions to handle the intermittency, the variability. A couple of years ago at GE, we announced an electronic gas hybrid turbine. And it's an integrated package of 10 megawatts of lithium-ion batteries with a 50 megawatt natural gas-fired turbine generator that are integrated together, that work as an integrated system with software that optimizes the operation of the two working together. Okay, so you have a very nice two solutions all packaged together, one for immediate instantaneous support, that's the lithium ion batteries, and the other for longer term needs, which is the natural gas fired turbine generator, all working together. So as time goes on, we'll see more and more new technology solutions to address the variability. Okay. Now, I mentioned voltage regulation concerns, and this is an article I wrote over 8 years ago in Power Electronics magazine. And if you get on the internet and search Power Electronics magazine in my name, John McDonald, you will find this article. It's a very interesting study. I worked with San Diego Gas and Electric and Arizona Public Service, two utilities in the western part of the United States. And they were the first utilities to experience this. And what we're talking about, remember I said that policy is the strongest driver to encourage a customer to buy technology. Well, policy in the states of California and Arizona at the time strongly encouraged, made it very attractive for homeowners to install photovoltaic panels, solar panels on the roof of their home. Very attractive. And so many residential customers did this. And let's take what I did in this article. I took one specific situation in San Diego, California, with San Diego Gas and Electric. It's a distribution feeder that brings electricity to very nice homes along the Pacific Ocean. Okay. Now, I think as you know, in a substation, there's what we call an online tap changer. And remember I said that we want the voltage at the customer's home to be within a certain range, right? But we also want that voltage to be steady state. We want it to be constant. Because if it isn't, if it changes quite a bit, as an example, the light bulbs in your house will be very bright and then very dim, and then very bright and very dim. They'll be changing all the time as the secondary voltage fluctuates. That would drive us crazy, right? So a tap changer, as the primary voltage fluctuates, changes, the tap changer changes settings to keep the secondary voltage constant. So the more volatile the primary voltage is, the more times the tap changer is operating. Now remember, a tap changer is a mechanical controller. It's mechanical. So the more times it operates, the more frequent it operates, its lifetime decreases, right? It wears out. It's mechanical. So for this feeder in San Diego, originally, the tap changer was operating maybe 5 times per day. Okay, so it was a fairly steady state condition. Now all of a sudden, many homeowners install rooftop solar panels. In fact, over 35% of the homes on one feeder installed rooftop solar panels. Now these homes are along the ocean, which because of all the moisture in the water, in the ocean, it was very foggy in the morning. So we say it's a marine layer of fog due to the sea, to the ocean, and which would block the sun's rays. As the morning progressed and the fog burned off, all of a sudden, all of these homes began generating at the same time. When those solar panels first saw the sun, when the fog burned away, they all began generating. The voltage on that feeder spiked. When all this generation began, it spiked and then it began to oscillate. This tap changer is trying to keep the primary voltage constant, and it's operating now over 120 times per day. And its expected lifetime went from 35 years to less than 2 years. Less than 2 years, okay? So the reason I wrote this article for Power Electronics magazine, I said we have new applications of power electronics needed for the grid. One example is an online tap changer. As we implement more renewable, more distributed generation, and the penetration increases, we aren't able, it's not feasible to use mechanical controllers anymore. Their lifetime is too short because the grid will be much more volatile with voltage and reactive power. A second application is low voltage network dynamic grid edge controllers. We're developing, it's low voltage power electronics. And these are set point controllers that we install at the edge of the grid where we have a high penetration of photovoltaic panels. And the third is smart inverters, increased capability from inverters. So these are three examples of low voltage power electronics that we need for the grid. Okay, so at universities, and with companies, I emphasize that we need power electronic experts to work more closely with power system experts. In the IEEE, we need a closer working together of the Power Electronics Society, which we call PELS, P-E-L-S, Power Electronics Society, with PES, the Power and Energy Society. Okay. So it's a very interesting article. And at the beginning of the article, you can find online, I show the voltage waveforms from this feeder at the time when the sun first appears and all these houses, all these solar panels begin generating. Okay. So I said many utilities are installing advanced distribution management systems today, and it's because of the increased complexity of the distribution part of the grid. So this is the centralized. This is the model of an ADMS, Advanced Distribution Management System. And you can see that there's a basic SCADA platform, and then there's all the applications here, feeder automation application server to optimize the distribution part of the grid. All the substation feeder devices send the real-time data to the ADMS. The applications analyze it and figure out how to optimize the operation, and then device control commands go back out to the field to do that optimization. So in any ADMS, there's three groups of applications. There's the real-time group, and these applications operate all the time. And this is what the operators use to monitor and control the grid all the time. Now, if you're interested in this, another fellow, a friend of mine in IEEE PES, and we teach a one-day tutorial just on ADMS, and it's available on the IEEE PS Resource Center. It's 5 different PowerPoint files that we use in the one day. And actually, at the beginning of COVID, about a year and a half ago, the IEEE PS made our tutorial available for free because people were spending more time at home. And the IEEE PS offered, one of the tutorials they offered was ours for free. And it's available on the IEEE PS Resource Center. So the first group of applications is real-time. The second group is what we say on-demand analytical applications. We use for certain specific applications like short circuit studies, optimal feeder reconfiguration after an outage, the optimum location to install capacitors on distribution feeders. The distribution power flow here is really today both a real-time application and an analytical application, right? It gives us the ability to model the distribution system on a full three-phase unbalanced basis and simulate different the impact of different actions. And then the third group is ancillary or additional applications that the utility wants to run. Okay. Now, I said that the goal of utilities is to be fully digitally enabled, or the digitized grid. But no organization can do that in one step, right? Too costly, too much money in one step, and also you need a lot of expertise and people to do the installation of the equipment. So what we do is we help utilities put a roadmap together on what steps make sense to go from where they are today to the fully digitized grid. And so let's show an example roadmap here. Here's a utility that today has manual control and legacy methods, a manually operated network, and a static view of the network configuration. Not dynamic, but a static view. So, whoops. Huh. Okay, so the second step is these next two here: customer status with trouble calls and smart meters with metering communications. This is automated metering infrastructure and circuit reclosers. The third step is network visualization tools, outage management prediction, and remote control and monitoring. And the fourth step is network optimization, utilization, and asset performance management. And the important thing is that with each step, there should be significant benefits back to the utility. Okay? So the second step would bring us 28% lower customer minutes interrupted. That's significant benefits. The next step would give us 43% lower customer minutes interrupted over the base level. And when it's fully digitally enabled, much greater than 50% lower customer minutes interrupted. So you can see this is a reasonable set of steps, reasonable budget money, reasonable resources required, but at each step, significant benefits back to the utility. Okay? And here's a case where we have a large utility with 856 distribution circuits, and they want to improve the reliability. But, you know, the question is, do we need to automate all 856 circuits? That's a lot of money, tremendous amount of money. And let's study this. And when we study it, we find that only 23% of the circuits account for 71% of the outage minutes. So this makes more sense here. If we automate just 200 circuits, or 23% of the circuits, we're accounting for almost 3/4 of all the outage minutes. So it's a much better use of the money. Okay. Now, to get full value of our investment in protective relays and microprocessor-based devices, there's two types of data in a microprocessor-based device. And what we typically focus on is only the operational data. That's the real-time data that the operators in the control center use to monitor and control the grid. And it's things like real-time status, performance, and loading. And these are points of information and a time series of points. Could be circuit breaker open close, could be current, voltage, real and reactive power, could be alarm information. But this is what we've used for many, many years. And we collect in the field and send up to the control center. But when we started seeing microprocessor-based devices for the first time in the 1980s, they gave us a different type of data that originally we didn't know how to use. Now, I wrote an article in 2003 in IEEE Power and Energy magazine. That's the magazine for IEEE PES members, and introduced the concepts of operational and non-operational data. The non-operational data gives us a lot of value, but it's not a time series of points. It's on-demand points and data files. And the primary user is usually someone other than the operator. Could be asset management, could be maintenance, could be power quality, up to 25 to 30 groups within the utility. And this is like maintenance information, information for the protection engineer. And it could be a digitized waveform, could be a sequence of events report, so it could be a file or points. And the operational data is typically, as I said, a time series of points, real time or near real time, and we always use standard non-proprietary communication protocols. The non-operational data, points or a file, mostly historical, it's trends over time. And if it's a file, we may need the device vendor's proprietary format to extract it, which is not a problem today. So we'll get back to this in a minute with respect to enterprise data management. But what's very important in addition is the Internet of Things. So it's really a productivity revolution, and with greater connectivity through communications, as we talked about, we're combining intelligent machines with big data and analytics and with people. And we're connecting people any place, any way, anytime for intelligent operations. So the end result is we have much greater connectivity, but we also have more compute capability. We have more data available. We have new analytics to analyze that data and provide us new value. And people have the data that they need more readily available. Okay? So the advantage of that is on the left here, what we're showing is a typical situation in a utility today, which is not good. It's a siloed way of operating. And what I mean is each group in the utility, like the protection group, the planning group, they have their own systems, their own devices, and their own databases. And there's no sharing, okay? On the right is what we want and what we help utilities do is break down the silos and let's have data sharing of all the systems, all the devices, and all the repositories. And we do this by adding a federated data mart in the enterprise. And we look at all the operational users in the control center and the non-operational users, and we look at all the data sources, and we make sure that all the data that's needed by these users is identified, extracted, and communicated to them. Okay? The advantage then is we're realizing greater value from the data. On the left here, we're showing a standard architecture of a substation of master data concentrators, slave data concentrators, and collecting all the operational and non-operational data from the intelligent electronic device. This is a term we came up with in the IEEE in the early 1990s when we were updating IEEE standard C37.1, which is the IEEE standard on SCADA. And intelligent electronic device is providing both operational and non-operational data upstream, as we talked about. On the right here, in light blue or cyan, the color cyan, we're showing all, we want to show all the data sources in the enterprise. On the right in green, we want to show all the users that have a need for additional data. And if they have that data, they can provide more value to the utility. So the goal is identify all the data that has value and all the data sources in the enterprise and make sure that all the users get the data they need. Okay. Now, this slide is very important because this is the journey to digital transformation. One of the 5 books I've co-authored is a new book we did a couple of years ago called Big Data Application in Power Systems. And we're showing how the use of artificial intelligence and machine learning and this digital twin concept can take us from reactive to responsive, where today we're really at predictive, but we're only halfway along the journey. we want to eventually get to prescriptive and autonomous operation of the grid, which is self-healing, self-provisioning, and extensive autonomous operation with limited human intervention. This is really exciting because we've made a lot of progress to move from reactive to predictive, but we're not yet fully doing predictive, fully getting the full benefits. And then we're only halfway to where we can be. Okay. That's why we're hiring a lot of data scientists today. And there's much more emphasis on artificial intelligence and machine learning. So wrap up here with a couple final concepts. One is industry standards. And, I showed in these holistic solutions, these technology components need to be able to successfully be integrated and interoperate with each other. But the thing is, to do this, we need compliance to the same standard or sets of standards. And even though there's hundreds of standards, industry standards out there with respect to smart grid, I chaired a board of 25 industry experts for 5 years. And we went through all these hundreds of standards. And we wanted to make it easier for industry. And so we said, these 16 standards are really the most important with smart grid. These are the foundational standards for smart grid. So you don't have to think about going through hundreds of standards. Just focus on these 16 and you'll find the standards that are relevant to the work that you're doing. And what makes it easy today is there's one standard worldwide for communications from control center to control center. There's two standards worldwide from control center to field, whether it's a North American supplier or European supplier. And within the field, there's really one global standard, IEC 61850, but in North America, we still use a lot of what we call Distributed Network Protocol 3. So one thing that's important, as you implement technology, it's good to stop, reflect back, and say, what were my initial assumptions? What have I learned? And what changes will I make going forward? Okay. So these are some of the lessons we learned initially deploying smart grid projects. A smart grid solution is a set of technology components. The maturity of that integrated solution is only as mature as the least mature component. If you think of a chain is only as strong as the weakest link in the chain. If you pull the chain and it breaks because one link was weak, then the whole chain breaks, right? So it's the same with a holistic solution. So you really want to look at your component technology and look at the maturity of each of the components. And initially, in many cases, some of the components we had to field re-engineer or upgrade to meet the objectives and expectations. Secondly, integration and interoperability. I keep saying that, but it's very important. And we realized how important standards were for successful integration and interoperability. Third is testing. You can't do enough testing in the factory. You need to do as much testing as you can before you get to the field. And you need to do end-to-end testing, right? From the device in the substation up to the control center for the office. One thing we found was project management is extremely important. As a supplier, we could provide the best technology to the customer. The customer could have the best engineering team, but if the project manager was weak, the project could fail. Okay, so the project manager was very important, and the project manager needed multidiscipline authority. A smart grid project involves so many different groups in the utility that the project manager needs to have authority over each of those groups for a successful project. And each of the project managers needs to manage in a consistent way, which means that there needs to be a program management office with consistent project management guidelines. Also, as I said, each customer, we need to help the customer build an A team. In other words, have the very best project management and engineering members, because there will be challenges to solve in the field. And then lastly, um, one thing we found with Smart Grid that we didn't expect was a new major stakeholder was the residential and commercial customer. The end customer now is a very, very important. You can't put a smart meter on somebody's home without engaging with them and explaining to them what are the new services we're providing, and making sure that they understood the new capabilities that they had, and giving them access to their use information from the smart meter. Okay, so it's a lot of material. I appreciate being able to go through that with you. I'll stop sharing. Uh, and if anyone has any questions, or any comments, I'd be happy to, discuss those. Okay.
Yeah. Yes, sir. Thank you. I would like to ask the participants, like if they have any queries, they can put in the chat box or they can unmute themselves and ask directly. We can have one. We can wait for 1 to 2 minutes for that.
There's something in the chat already. Um, so the name of a site or a course from where we can learn more about smart grid. Let me give you a couple. I would say there's three sites that you could look at. Um, and I have courses and webinars on all three sites. One would be IEEE PES Resource Center. Okay, IEEE Power and Energy Society Resource Center. Second would be the IEEE Smart Grid portal. There's a website. I've done a lot of many of us have done a lot of webinars for IEEE Smart Grid. And third would be IEEE Educational Activities. I did a series of 4 1-hour courses on Smart Grid, 4 different parts of Smart Grid, um, for IEEE Educational Activities. These are beautiful courses with a professional narrator, professional graphics. I wrote the script. I put the graphics together, but they was professionally done by IEEE Educational Activities. And those 4 different courses are available. Okay, so that's 3 sites. And then I've co-authored 5 books, and these are all practical references. One is, I mentioned, one is Big Data Application in Power Systems. The second one is a book on Smart Grid, second edition, over 800 pages. Third is the most practical reference book today in substations. It's called Electric Power Substations Engineering, and it's 22 chapters on all aspects of substations. Okay. Fourth one, I mentioned Power Systems SCADA and Smart Grids. So those 4 references are very, very good references. Now, the substations book is one of 5 books, and we package those 5 books, and that's called the Electric Power Engineering Handbook. And so my substations book is one of 5 books that are packaged together in the Electric Power Engineering Handbook. And when you buy those 5 books, you spend a lot less money on. It's what we call bundled pricing. When you bundle the 5 books together, it's a very reduced price for the handbook. So you can find all these online, the Electric Power Engineering Handbook, and then the names of the books that I gave you. So that's some examples of some good references. Okay.
Sir, there are a couple of questions in the chat box. Can I like read out for you?
Yes.
Yeah. In the future, there is a question from Aviti. In the future smart grid, what do you think is the contribution of nuclear power in the face of increasing renewable injection to the grid?
I, you know, I would hope, that we would see growth, truthfully, growth in nuclear power. Um, I mentioned non-variable, or I mentioned variable generation helps the environment, but it is a challenge from the point of view of regulating the grid because it's variable, right? And we can't just have full PV panels and wind generators, but we have to have something behind it because of the intermittency. And what I mean behind it is like energy storage, natural gas fired turbine generators that start quickly and respond quickly um, to changes in intermittency. The advantage of nuclear power and large thermal power plants is that we can base load those. I mentioned that. You can put its output at a certain level and it'll stay there. We also these are the not a nuclear plant, but a coal-fired, oil-fired, a thermal plant. We use those to regulate the grid every 2 seconds, right? With automatic generation, with AGC, automatic generation control. So, but the challenge is, and is nuclear um, has a lot of regulations. Um, has in the United States, for instance, it's a multi-step licensing process. Um, and because of all the steps required, there's more risk with it, more risk from a point of view of cost overruns, schedule delays, and because of that risk, um, utilities and organizations know that there's advantages to nuclear power, but the risks are so great that they avoid nuclear power. So it's too bad. I wish it was more attractive, and I wish there was more focus on nuclear because we really need more baseload generation, and nuclear is ideal. Um, but I'm afraid that the licensing, the risk, have made it too have made it too risky, and it's being avoided in many countries in the world.
Sir, there is one more question from Said Salimi Amiri. The question is it possible in practice to have a large domain distributed battery electrical energy storage devices throughout the grid?
Well, that's really what the trend is. Um, so that's what we have to deal with. It's happening, you know, whether we like it or not. It's happening. So that's why the distribution part of the grid is so different today than it was. I started my career over a little over 47 years ago, my full-time engineering career. And, it wasn't, I did a lot of international consulting from 1995 through 2007 before I joined GE. And when I would ask the supervisor of the control center at a utility, I would say, you have a SCADA EMS or generation transmission. When will you um, when will you when will you implement a DMS, a distribution management system for distribution? And many times the supervisor would look at me and laugh and say, John, my distribution system is so simple. Um, there's electricity flowing in one direction. The architecture is radial, which means the feeders go from the substation, they bring electricity to the customers, and at the last customer, the feeder stops. So it's a radial topology or radial architecture. I don't need to spend money on a SCADA system for distribution because it's so simple. That has completely changed, as I mentioned. We have with integrating distributed generation now all throughout the grid and energy storage. We have electricity flowing in two directions. We have many challenges today, much more complexity, and the need for a DMS or ADMS is great. You know, they're needed to manage the complexity and optimize the distribution part of the grid. So that is the situation we have, what you described, and we have to deal with it. We have to make the best of it. We have to optimize it. We don't have generation anymore. We don't have centralized generation anymore. It's fully distributed generation, and all throughout the grid, whether it's transmission level, distribution level, or at customers' premises. You know, that's the real world, and that's what we have to deal with.
Okay, sir. There is one more question from Vishal Kumar. For the future smart grid system, which power generation is the best suitable for us?
Um, well, I mean, you know, the the one form of variable generation where the cost has become very low is solar. And that's why we see so much solar. The other thing is we can implement solar in a transmission level, distribution level, or at a customer's home, right? So it's very attractive from that point of view. Now it's easy to implement. The attractiveness comes from the policy. Um, for instance, in California, the policy was when you bought electricity, you paid 10 cents a kilowatt hour. But if you generated your own electricity and sold it back to the utility, they had to pay you 40 cents a kilowatt hour. That business case is very attractive. You know, the wider that spread, the more attractive the business case is. And that caused many homeowners to purchase or had to install photovoltaic panels on the roof of their home. So I would say the most attractive right now variable generation is solar. Wind, you really wouldn't put wind at your home. You really wouldn't, wind is you don't see individual wind turbine generators. You really see like wind farms because of the cost nature. It's more it's more attractive cost wise if you have a number of wind turbine generators in a wind farm. But there you're getting in, you're coupling that into the transmission system or a higher voltage part of your distribution system. So wind is not, in general, is not as attractive as solar. So we see a lot of use of solar today.
Sir, there is one more question from Dharmendra Yadav. The question is, what are the efforts towards securing the grids from cyber attacks?
Yeah, that's something that we study and we implement every day. Um, when we develop new technology today, uh, cybersecurity is a very important part of that. Um, when we develop SCADA systems, very complicated integrated software and hardware systems, computer-based systems, uh, we actually we actually in the United States we send those to a special laboratory, government laboratory that has professional hackers, people that are very skilled at doing penetration testing of a SCADA system. And so we're constantly testing, looking for vulnerabilities, whether it's a product or whether it's an integrated system, looking at the possible vulnerabilities and not just ourselves, but hiring outside people whose expertise is in that area to do that testing and try to identify all the vulnerabilities and take care of those, address those before the technology becomes a commercial product. Okay, so we're doing everything we can. There's a lot of focus on that, and the important thing is that focus is from the very beginning of the development of the technology throughout the development. Um, so a lot of emphasis on it, a lot of focus on it, and we're doing everything we can, and we're learning. For instance, I give a separate talk on cybersecurity, and I go through the 3 or 4 years ago, what happened in Ukraine, where hackers spent 9 months collecting information and planning the attack. They launched the attack with three distribution utilities, and caused over 225,000 people to be without electricity for an extended period of time. So the thing is, when things like that happen, we really need to study that. And I go through the anatomy of that, 25 different steps of what the hackers did over a 9 month period. And then when they launched the attack, and at every step, we think about how could we have prevented this from happening? What do we need to do in the future? And so as I go through that in my talk, we discuss what could we have done to prevent that. So we're constantly learning all the time. Also, how we can do a better job of protection. Very, very important topic, and tremendous focus today by everybody.
Thank you, sir. There is one more question. Like there are some research done to keep the voltage in steady state in microgrid, considering the increase of renewable penetration using BESS. These research were not practically employed, but it was done only in simulation. In your career of BESS, in your career, was BESS used to keep the voltage in steady state because of renewable penetration?
Yeah, that's BESS is battery energy storage system, and it's what's important is the batteries themselves require support equipment, right? And so if you take the batteries themselves and all the support equipment needed around the batteries for an integrated system, that integrated system is called a BESS, a BESS, battery energy storage system. And yeah, as I mentioned, um, one, you know, one very popular and very widely used way to handle the intermittency, to maintain voltage, and to make sure the electricity still is flowing to the customers even when the sun isn't shining or the wind isn't blowing, is with BESS. Um, now, the thing with batteries and with energy storage is that we still need more research to be done to bring the cost in general of energy storage down, because there's many applications of BESS or energy storage where the business case, the cost is a little bit too high. It's not as attractive as it should be in general. So there's still a lot of work going on. Different, as I mentioned, different chemistries, lithium ion, sodium sulfide, flow batteries, a lot of different types of energy storage. But we need to do a better job of bringing the cost down for BESS, and so it's more attractive. Let's say to increase the attractiveness, so it's more attractive with all the different applications of BESS. And remember, those applications have different time frames. I mentioned it could be more of a power application, which is instantaneous, like frequency support, versus a longer time application, which is more energy related. And so we We need the chemistries, we need the different best technologies to handle the full time domain of applications, right, that we have in a cost effective way. And so there work is going on, and we need to make more progress in that area. But it's you know it's a very important way to maintain voltage, to address the intermittency, and we need it. We absolutely need it, but we need the cost to come down more in the future.
Thank you, sir. I hope there
Okay.
are no more questions from the participants. Then I can share my slide.
Okay.
Yeah. Uh, so on behalf of the IEEE PES NIT Calicut student branch, I would like to thank you, sir, for accepting our invitation to be a part of the webinar session and spending your valuable time and efforts in educating the faculties, research scholars, and students from various colleges and working professionals. Thank you, sir.
Thank you for the invitation and the opportunity to be with you. And I wish you the very best of success in your futures. Okay.
Thank you, sir. And I would like to request all the participants to kindly fill up the feedback form. The link is there in the chat box.
We are inviting our suggestions too for the improvement of this webinar series. Thank you. Thank you, sir. Thanks once again. Thanks for us. Thank you.
Thank you very much.
Bye.
Thank you, sir.
Bye.